Good evening, everybody. We're doing a problem that deals with this notion of order, which is a very important notion in number theory. And we're going to show you that some computational value right here. We're just arbitrarily picking p is equal to 19. And we're given that a is an integer of order 6. Okay? And what that means is that a to the 6th power is the same thing as 1 mod 19. Now this is a general notion, I'm using specific moduli here. Mod 19. And the notion of order doesn't require that the modulus be prime either, okay? And that should be 1. Okay, now this is important because once you get to 1, the thing tends to repeat, or it does repeat. But in any event, let's just use a concrete example right here. Let's do, let's say 8, okay? So let's take a look at 8 squared. Now 8 squared is equal to 64. But notice that's congruent to 7. And, I'm not going to write down, but it is mod 19. This is the congruent symbol, and it's understood to be mod. I'll write it down one time. Okay, mod 19. Now, the reason why that's true is that just think of it like this. 64 minus 7 is a multiple of 19, namely 57. 64 minus 7 is 59, and 3 times 19 is 57. 57 can be thought of as 0 also in the modular, in mod 19 speak now. Now, from here, we're still trying to get the order. You see, this is not equal to 1, right? So notice that this follows, and hopefully I'm not leaving too much out here. 8 to the 6th is the same thing as 8 squared cubed, right? So this would be congruent. You can treat congruency just like equality in most cases. Okay, so this would be 7 times 7 times 7, right? And again, we learned up here that 8 squared is 7 modulo 19. Okay, so if you cube this and you cube this, you get this statement right here. Okay, so you can treat congruence like equality in many cases. Okay, now we can reduce 49. Let's see, this would be congruent to, what's 49? 3 times 19 is 57. Or no, wait, we need 2 times 19, right? 2 times 19 is 38. So 749, let's see, that's congruent to 11 times 7, right? Okay, but notice this is 77. That is equal. We can use equal instead of, but notice this is congruent to 1. Okay, it's congruent to 1. Again, mod 19, because 77 minus 1 is 76, and 4 times 19 is 76, right? So what we know is that the order of 8 mod 19 is 6, okay? And I chose this just because it's numerically related to this more general thing where we have a as an integer of order 6 modulo p, and we want to calculate the value of this, and I should say mod 19, okay? I should say mod 19 here. That's a mistake on my part. We want to calculate this value mod 19. I should have put just mod 19 down here, I guess, okay? But in any event, let's take a look at what this means. Summation a sub I is equal to a plus a squared plus a cubed plus a to the 4th plus a to the 5th. Now notice that an important fact here, we have a cubed is congruent to -1. That follows from the fact that a to the 6th power is 1, okay? And so it has to be equal to -1. Otherwise, if it were 1, then a cubed would be the order, right? But we've shown right up here that 6 is the order, right? 6 is the order. Okay, so we're stating that 6 is the order. It has nothing to do with the numerical example. I'm sorry. Okay, but we know that, you see, a is known to have an order of 6 just generally for this problem, and so a cubed couldn't be congruent to 1 because that would say that a had an order of 3, right? But if you cube both sides of this, you get a to the 6 is congruent to 1, right? Which is consistent with this having an order of 6, okay? Now, what does that do for us here? Well, this makes life pretty easy here because I'm going to do a computation here, modulo p, not 19. The 19 was just an example. So no changes here, no changes here. And I'm doing mod 19. So I'll write that at the end though. Okay, so a cubed is -1 plus -1. Now right here, notice that this is a cubed times a to the a, right? So this would be minus a. Now notice this is a cubed times a squared, so this would be minus a squared. And again, we repeatedly use this fact. Okay, now let me put mod p, not 19. That was a little confusing what I said earlier. So this is true. Okay, and that's what I meant, calculate the value of this mod p. But you can see that everything cancels. The a, now almost everything. The a terms cancel, and so what we get right here is it's congruent to -1. Okay, so this is congruent to -1 mod p for any p where so this is a more general statement than what we started with. Okay. Now notice this is really the same thing as p minus 1 also, since p is congruent to 0 mod p, right? You can call it -1, you can call it p minus 1 if you want, and we're trying to get it reduced, I guess. But anyway, I guess the hardest part was writing this down, okay, because it did follow from the fact that a to the 6th, kind of taking the square root, if you will, in a manner of speaking, a to the 6 is congruent to 1. That's given, right? This is a given condition. So we can't have a cubed is congruent to 1, otherwise that would contradict the fact that 6 is the smallest exponent such that this is true, right? So we have to have this. When you cube this, you get back to this statement, right? So you can think of it like square root if you want to. You don't really have to get too formal about it, But in any event, this is the solution to the problem right here. -1 is the answer to the question, folks. And I hope that was comprehensible. I hope I didn't. I kind of mixed up the that should be -1. One thing I would like to say right here, you can go back and verify this if you want to for this case, this special case. Go back through and substitute it in and do the numerical reductions, and you will get -1, or you'll get 18 as well. 18 is congruent to -1 if you're dealing with modulo 19. But the general, let me just write this in here again. This is congruent to -1 mod p. Okay, that's all.